Okay, so let's get started. So this class, we're going to finish the discussion of the aerosol size distribution measurement using the scanning mobility particle sizer, or using similar mechanisms that is using the electrostatic force to classify the aerosols. Okay, so if we do a quick recap of our last class, so last class we mainly discussed this transfer function, right? So we basically showed how the DMA is actually not classifying particles of the same size, right? And we discussed the resolution of the transfer function, right? So the transfer function is a triangular shaped function, right? When the aerosol flow match with the sample flow. And also we discussed that for the small particles, because of the diffusion, there's going to be a broadening effect of the transfer function. We also discussed that the charge distribution is going to affect how the SMPS measures the size distribution. So in these SMPS systems, we use the bipolar charger to basically monitor, to charge these aerosols, and then we use the Fuchs theory to predict what is the charge distribution onto the particles. And then we discussed that there is this data inversion process where we convert the measurement that's collected by the CPC to the original aerosol size distribution, right? So basically, if we just go through this data inversion process again, so there will be factors to determine the CPC reading in this size classification process. There's this effect of the transfer function, the charging efficiency, the CPC particle detection efficiency, because not all the particles are being detected by the CPC. And then there's also the sampling loss. So to consider all of these effects, then basically the response of the CPC is going to be an integral of all of these factors, right? So as you can see, it can be shown as this equation here. And further, if we assume that there's no multiple charging, which means the particles at maximum, they can carry one charge only, either positive or negative, then you can remove this summation sign here. And further, you convert this dn to, let's say, multiply the terms both on the denominator and numerator, numerator. So basically, you're converting that to the size distribution, this size distribution function here. And further, these functions can just be determined by the relationship between particle size and the mobility, right? So you have the expressions for these different terms, and then you can calculate what's the derivative here. And because of that, these terms can be further seen as constants. For example, the CPC detection efficiency, the size distribution, right? Size distribution is basically here, and then charge distribution is here. You can treat these terms as constants in the narrow range of the transfer function, because eventually you're integrating using the value of the non-zero section of the transfer function, right? If the transfer function, if we're talking about the area outside the transfer function, then this integral will be zero, right? You're only considering the values where the transfer function has a non-zero value. So you can move these relatively constant terms out, right? And then you have this integral of the transfer function here. And further, this is a constant. You can directly move it out. Then you just have the integral of the transfer function, which is the area of the transfer function. And as we introduced earlier, the transfer function has a base of 2 beta, right? When you plot it in the normalized regime, right? Base of 2 beta and then a height of 1. So the area of the transfer function is just a beta, right? So further, you can rearrange this to calculate what is the dnd log dp, right? So just move it, keep it on this side, and then move everything onto the other side. Okay, so and this is the solution when you're assuming that there's no multiple charging. But there's also a scenario where you have multiple charging. And under that situation, you have to consider how the multiply charged particles are contributing to the response of the CPC. So here I'm just writing the entire equation here. So again, you need to consider the size distribution, the particle penetration efficiency, the counting efficiency of the CPC, and also the bipolar charging probability, right? So I here represents how many charges are carried by the particles. So this is a charged fraction. and then you multiply that by the DMA transfer function. And when you have two charges, then basically you also need to calculate the transfer function for the multiply charged particles, right? So this is going to be a summation of all the different charges. So then under this situation, how do we solve that? Again, one thing I want to point out here is that it should be dn in the beginning, and then since we multiply we divide that by d log dp and multiply that by d log dp, so you directly have this dn d log over d log dp as the n dp here, right? So we can do the similar things. So basically, first we will separate this summation sign to different size bits, right? Because here it represents a log dp term, right? So basically in dp term, you can separate them into the summation in all the different size ranges. So basically from the smallest size bin to the largest size bin. And further, we could make the assumption that the aerosol concentration in different bins can be treated as a constant. So if they can be treated as a constant, you can move this particle size distribution outside this summation sign here. Okay, so you have this term here. So basically, now the response of the CPC is just the summation, right? Summation of K terms. So basically, K represents the size bins you use. So what this is showing is that the response of the CPC is determined by the aerosol size distribution in these K number of size bins. And for each size distribution, you need to multiply it with a factor here, right? This factor here is just the integration of all of these factors included, right? So if you write it in another way, so basically if we do multiple measurements at different sizes with the SMPS, right? And then you're going to have multiple responses by the CPC. So if you write it out, then the measured response of the CPC is basically determined by the multiplications of all of these factors. Okay, you have these size distributions, right? And then you multiply that by these factors over here. Okay, this is a summation considering all of the transfer function, the counting efficiency, and the CPC detection efficiency, right? So then it comes to the question of, if we know the measured responses and we know all of these factors, how do we find out the size distributions, right? So this involves the calculation with the inversion matrix. Basically, this is what we call the inversion process. That is to find the n, which is a column here that gives you the measured responses of the CPC. There are different inversion methods, and this is actually a classical problem in the, let's say, the matrix calculation, right? So you cannot directly get or use the solution to this equation, because sometimes you may have negative size distribution. So you have to find the size distribution that has non-negative value, but also give you the smallest error that fits this equation here. Okay, so there are two commonly used methods. One is called the Toomey inversion method. It was first developed by Toomey in 1975, and then it was further improved by Markowski in 1987. And there's another method that's called the non-negative least squares matrix inversion that's made by Lawson and Hansen in 1974. So by using these data inversion methods, you can calculate what is the size distribution based on this inversion matrix here. Okay, this is the more, I would say, the more accurate inversion method, because as we introduced earlier, the only reason why we use this inversion is because of the multiple charging, right? We also mentioned that for particles above 100 nanometer, multiple charging is becoming an issue. More particles are doubly charged or triply charged, and then you're going to affect what you're going to measure from the size distributions. Okay, so basically now we have covered the data inversion process of the SMPS. But one thing we want to mention is that basically here, we assume that when we operate the SMPS, we give it a voltage and then we record a CPC reading, right? We move to the next voltage and then record the CPC reading. So basically, we're assuming that the SMPS system is operated under this stepping mode, right? So you gradually increase the time or increase the voltage, keep it for some time, and then move to next voltage, and so on. you can see there's a clear issue with this stepping mode, right? That's basically this measurement is very time consuming. You have to keep the CPC or keep the DMA voltage there for a sufficient long time so that you have a steady state or a constant flow of classified aerosols going to the CPC, and then you record the value, right? So because of that, people invented new methods to operate the DMA, that is the scanning mode of the DMA or the SMPS. So in the scanning mode, the voltage continuously or smoothly increase exponentially, right? And then it can also do this down scan, or you can call this up scan here. And then you can also do the down scan, where the voltage can exponentially decrease all the way back to like the beginning voltage, right? So because of this scanning mode, then we need to consider what's the response of the CPC. So we mentioned earlier that the particles are also always going to take some time for them to transport to the CPC. And more importantly, inside the CPC, the particles near the wall and the particles near the center of the growth tube have different resonance time, right? So particles near the wall of the growth tube, they have the smallest flow velocity, which means that they're going to stay for a longer time. So this means that when you are scanning the voltage, for example, when you move here, when you first reach the voltage of 100, right? And when the voltage, basically the DMA classifies particles corresponding to this size, but it takes time for these particles to reach to the outlet of the DMA and further reach to the detection part of the CPC. So by the time the CPC detect these classified particles, the DMA already moved to the next voltage, right? So how do you correlate this concentration here that you measured at this voltage to the value that you measured over here, right? So basically, this is the issue with the upscan and downscan of the SMPS systems. So we call this effect as a smearing effect. So it's kind of like mixing the aerosols, that you don't have a high resolution in detecting the aerosol sizes or detecting the concentration of the aerosol sizes, right? So for example, here we're talking about the upscan condition, right? So let's say this is our original size distribution, okay? If you do the upscan, it means that you're classifying particles over here, right? You're classifying, let's say we're classifying particles at this location here. And then we're doing upscan, then it means that the voltage is scanning up, right? So when the voltage is corresponding to a higher voltage, it means that it's already set up to be collecting larger particles. But then because of the smearing effect, there's resonance time of the particles in the system. Even the voltage is already above this, like the size corresponding to the lower voltage, you are still detecting particles, right? So because of that, if you check the voltage that has the mobility that has a smaller value corresponding to this default value here, which means the particles have larger sizes, further means that the voltage is under a higher value, then you're still detecting particles, right? So this will basically shift the aerosol size distribution to the left-hand side of when you are showing it in the mobility region, right? So the same applies for the downscan, right? If you're using the downscan, when the voltage moves to a smaller value, right, not corresponding to this aerosol that has a default size here, or the highest concentration here, but because of the resonance time, you're detecting particle at the smaller voltage, which means that they have a higher electrical mobility, right? So you're basically detecting particle over here. So, and this is related to how long, what is time you use for the scanning the size distribution. For example, if you use a long time, then you don't see this effect. But if you use shorter time for the scanning, then you have this smearing effect that will shift the aerosol size distributions, right? So because of that, we have to consider what's the response of the CPC, right? There's always this time for the particles to transport, but also the CPC response is going to have this exponential decay because particles in the CPC have different resonance time in the system, right? So if they are along the center line of the growth tube, they are being detected in the beginning, right? Most quickly. But if they're moving along the walls of the growth tube, then they're being detected later on. So because of that, we have to consider this resonance time or this smearing effect when we are trying to invert the size distribution. So there are relatively complex processes for doing this data inversion, but you can see after we consider this smearing effect, you can get relatively accurate size distributions compared to the case where you had this let's say where you have the case of a long time scanning, right? These are the corrections of the aerosol size distributions. So basically here, this is showing you the different resonance time of the CPC, right? So if you have different resonance times, then you need to do different types of corrections to consider this smearing effect. Okay, so now we're going to introduce some variations of the SMPS systems, right? So basically these systems are still using the electrostatic force to separate the particles, but they may have different geometries or they may have different types of functionalities. So until now, we introduced the SMPS system. So the SMPS is made of two concentric cylinders where separating particles based on different mobility sizes, and the CPC measures the concentration of these classified particles. You can see that to measure the size distribution, we have to scan the voltage with time, right? The CPC then measures the concentrations of different particle sizes, but there's a limitation. So generally, these SMPS systems are operated at a scanning time of 1 minute, right, for the size range between 10 to 1,000 nanometers or 600 nanometers. But there is an issue that when we're dealing with very rapidly changing aerosols, right, then the SMPS can't capture that. So one example can be, for example, the SMPS voltage is increasing, and when it's measuring these larger particles, then something changed on the smaller size range, right? But since the SMPS is operated under this high voltage here, there's no way the CPC can notice what's happening over here, right? So then this will cause some issues in terms of the time resolution for the aerosol measurement, right? So for most of the ground-based air quality monitoring or the aerosol size distribution measurements, this time resolution is not a big issue because if we consider the measurement over a year, right? So who cares what happens over a few seconds, okay? But there are scenarios where we have to consider this high or this resolution, time resolution for the aerosol measurement. So one example is the aircraft-based measurement, right? These research aircrafts moves with very high speed, 100 meters per second. So if you have the instrument that monitors size distribution every 1 minute, then the aircraft is already 6 kilometers away. You can't achieve, or basically you can't really notice what's happening over, let's say, a spatial regime or spatial scale of 6 kilometers. And also, sometimes these aircrafts will go over clouds. And if they go over clouds, and the cloud droplets will shatter and then produce tiny particles, right? It's just like breaking up the cloud droplets, and then you generate a lot of tiny water droplets. So these aerosols are not existing in the ambient environment. These are considered artifacts, right? So then if the aircraft suddenly go through a cloud, and then you have to basically scan, just discard this data because these are artifacts, right? It ruins this whole 1 minute of the aerosol size distribution measurements, right? So this is how the time resolution might affect the aircraft measurements. And it also works for the scenario where there is intense formation growth of the aerosols. And this is more related to the high temperature aerosol formation process. For example, we know that when we burn biomass, there's always these different regimes of combustion. There's ignition, there's extinguish process, there's smoldering of the biomass burning. So different regimes, they just happen in a few seconds or a few minutes, right? So you can't really use the SMPS system to tell what is occurring in these different combustion regimes. So because of that, we have to find some instrument that can have a high time resolution for measuring the aerosol size distributions, right? So the objectives are to design new instruments with high time resolution. If we can, we want to push it down to 1 hertz or down to 1 second with a resolution of 1 hertz. And also it needs to achieve a high accuracy in the submicron aerosol range, especially below 100 nanometer, because these aerosols have a very high concentration in our ambient environment. And also they can contribute to the cloud formation. And also they pose a health impact, right? So there have been some established or commercialized instruments to look at these high time resolution aerosol size distribution measurements. So one example is the electrical aerosol spectrometer. So remember we had this DMA column here, right? So instead of sending the aerosols through the, let's say, the classified aerosols through the inner electrode, so this instrument basically will put electrometers at different locations on the outer electrode. So the aerosols are being introduced from the inner electrode, right? So it's, compared to the DMA, it's quite different, right? The DMA has aerosols being introduced from the outer electrode. So here the aerosols are being introduced from the inner electrode. And then because of the electrostatic force, smaller particles move faster towards the outer electrode, larger particles move slower, right? So in this way, you get an automatic separation of aerosols based on their electrical mobility, right? And then you could further use the electrometer to record what is the concentration of aerosols with different sizes. So this is what people call the EAPS, the engine exhaust particle sizer, right? So there are also other types of instruments, for example, the TSI FMPS, that's a fast mobility particle sizer, or the differential mobility spectrometer, the DMS 500 by combustion, right? So they are all using this method that are classifying aerosols based on their electrical mobility and then measure their current by using electrometers and that are placed at different locations on the electrode. So this instrument can indeed achieve a pretty high time resolution measurement of the size distribution. But one issue is that it's using unipolar charging to give the particle charges. So unipolar charging has one disadvantage is that the charge fraction is not a constant. It's not as constant as the bipolar charging. So it's always dependent on how many ions you generate, what is the resonance time of the particles in the system, right? What is the concentration of the aerosols? So there's some uncertainty regarding the charge fraction or charge distribution with unipolar charging. The reason why they use unipolar charging is because they want to provide as much ions as possible so that you get enough signal on these electrodes. But another issue is that, as we introduced earlier in our classes, the electrometer are limited by the number of particles they can measure. Because right now, the electrometer with the best detection resolution can go down to one femtoamp. One femtoamp is 10 to the negative 15 amps, right? So if you convert it actually to the number concentration, right? So to achieve one femtoamp in these electrometers, you need at least, let's say, hundreds of liters per minute of the aerosol flow, which is not manageable by these instruments. So because of that, we still prefer something that are detecting particles based on their number concentration. And we go back to the CPC method, okay? So here I'll just introduce a little bit more on these electrical aerosol spectrometer systems. So similar to the SMPS systems, where you had the transfer function, these systems also have these issues. For example, when you're introducing aerosols with specific sizes, you're going to detect them in different electrometer numbers, right? Which means that they're being detected in different electrometers, right? So you have to consider these transfer functions when you're inverting the size distributions. And you can see that their transfer functions are also relatively broad, okay? So here, I will just introduce a relatively novel instrument to do these high time resolution size distribution measurement. Okay, so this instrument was developed by Jian Wang, my postdoc advisor. So it was first developed in his group, and then at that time, Dr. Pramod Kulkarni was a postdoc in Jian Wang's group. So they too started these building up these prototypes of the instrument to do these high time resolution measurement using a combination of the electrostatic force or the electrostatic classification and the condensational particle growth. So the instrument that they created, or they name it as the Fast Integrated Mobility Spectrometer, or the FIMS. So the FIMS is actually combining the electrostatic classification, condensational growth, and imaging, right? So they use a high-speed CCD camera to directly see these particles. So here I'll just briefly introduce how it works. So you can see the FIMS are treated as two parallel plates, or basically, if you consider the DMA, there are two concentric cylinders, right? If you consider these, the surface of these two electrodes, they are parallel to each other, right? So it's the same for the FIM system. They use a parallel plate DMA, where one electrode is connected to the ground, the other electrode is connected to high voltage. Then you introduce the charged aerosols, bipolar charged aerosols into the gap, right? This inlet slit here. So as you can imagine, the smaller particles move faster. They can move closer to the charged electrode. The larger particles move closer to the ground electrode. So you achieve the separation of the aerosols based on their electrical mobility. And then they will enter this totally grounded, what they call the condenser system. Okay, so here it's still, everything is still in the gas stream, but one thing that's different compared to the DMA is that in the DMA it has a clean sheath flow, but here in these in the FIM system we introduce the sheath flow that is saturated with some alcohol. It can be butanol, it can be heptanol, or some other types of alcohols. So then what happens is that in the condenser is connected to a, or basically you use these thermoelectric cooler to reduce the temperature in the condenser section. So then, as you can imagine, what happens is that, well, since you have a lower temperature here, then the butanol vapor or alcohol vapor are going to grow onto these particles. And since these particles are already classified here, and then the condenser is also grounded, then these particles will keep their original trajectory and just move, let's say, move with the sheath flow vertically downwards. And then at the end of the condenser, there's a laser sheet that shines horizontally across the gap between these two parallel plates, right? As you can imagine, the supermicron droplets will go through these laser sheets here, get illuminated, and then you have a high-speed CCD camera that takes pictures from the bottom, right? So basically, if you imagine, then you're going to see the walls of these two parallel plates, and also see the particles penetrating through this laser sheet here. And once they go through the laser sheet, they got illuminated, and you can see a dot over there, right? So basically, if you go look through the, let's say, if we look at this FIMS over this angle here, you're going to see this diagram over here. We first charge these aerosols, separate them based on electrical mobility, grow them condensationally, and then detect the particles size distribution, or detect the particles locations. So also here I have an animation of the system. So the aerosols are being charged. You separate them based on their electrical mobility, right? Based on their electrical mobility, and then they grow by the vapor condensation, and then the high-speed CCD camera will record the location for these particles. And further, you can imagine the distance or the location of these aerosols are actually related to the electrical mobility, because their movement is, or their horizontal movement is determined by the electrostatic force, right? And further based on the electrical mobility. And then the electrical mobility can be converted to particle size. So basically, if you have the location of the particles, then you know what's the size of the particles. And further, by counting how many particles are there at this, let's say, this line here, then you can calculate what is the concentration of the particles, right? So here, this is an example when we're introducing 100 nanometer particles into the FIMS. So you can see that these particles actually align on a straight line here, right? So you may imagine these particles are moving upwards or downward, but actually these aerosols are just entering this I would say this picture here, right? Because particles are moving this way, right? Moving downwards, and then you have the camera that's taking pictures from the below, right? So the particles are going through, once they go through this plane here, then they get illuminated, right? So also these high-speed CCD cameras can take pictures at very high time resolution. You can capture pictures at 10 hertz, which means that every 0.1 seconds you can take a picture and then calculate what's the size distribution. But one thing you can notice is that even if we send 100 nanometer particles into the films, excuse me, you're still going to see a distribution of the particles in this image. It's not a perfect, right? So the reason why we see this distribution is because of Brownian motion, but more importantly, it's because of inlet distribution, because the inlet is not infinitely narrow. There's always some aerosol flow. There's always the aerosol flow rate that will cause the expansion of the streamline, and then you're going to see a distribution of the particle location downwards, right? So later, we find out that basically, if we use a constant voltage onto this DMA and then just count particles from the, let's say, from this wall here to this wall here, then we can only achieve a like a 3-fold size range, okay? So basically, if you detect particles of 10 nanometer here, you can only detect particles up to, let's say, if you detect particles of 10 nanometer here, you can only detect particles of 30 nanometers here. But our goal is to try to monitor aerosols between 10 to 1000 nanometer. So how do we achieve that? We could build multiple fins, right? To make one cover 10 to 30, the other cover 30 to 90, and then 90 to 270. But that's too much cost and time, right? So we could also vary the voltage applied onto here. So instead of using a constant voltage, we could use like the SMPS, scan the voltage and then see the particle distribution. But then again, you are going to see the response issue and also the data inversion, right? So we don't want that, okay? So what can we do? So instead of using a constant voltage, what actually Dr. Jian Wang eventually did was that he replaced this constant voltage plate or electrode by these tiny traces of the electrodes, okay? So, and then for each electrode, it carries a different voltage. So for example, here the voltage is 10 volt, and then the voltage increase exponentially as you go to the next electrode and all the way to the end to 6 kilovolts. So now you can imagine, on this side, right, on the left side of the films, you're going to classify particles of smaller sizes because larger particles, they won't be able to move because their drag force is too big, right? And then on this side, you're classifying larger particles because now you have a higher voltage. So because of that, now if we send 100 nanometer particles into the system, you're going to see 100 nanometer particles here, but then gradually they're getting classified, right? So you can still, based on their location, to find out what's the size, and then count how many particles are near this trajectory here. So to relate that to the size distribution, okay? So for example, here, this is another animation showing you how the 100 nanometer particles, I would say their distribution looks like on the CCD camera. And then this is also how the electrode looks like. You see, there are so many tiny traces of electrodes that give you provide this electrostatic force, right? So further, we did a calibration of particles with different sizes. For example, we introduced 10 nanometer, 15, 20, all the way to 100, or all the way to 300 nanometers. So you can see particles with different sizes, they occupy different trajectories, right? And then by counting how many particles are there in different regions, you can convert that to the concentration or the size distribution, okay? So in terms of converting particle location to size, you can use the longevity equation basically to calculate where the particles are moving in their next time step. And then by combining these equations to eventually predict where they're located at. Or you could directly use this calibration results to relate to the particle location, to relate particle location to the particle size, right? But then it's more tricky to convert particle counts to number concentration. Remember, for the SMPS system, we need to do similar things as to convert the CPC reading to the size distribution, right? So here it's the same. We have to do an integration to consider the penetration efficiency, charging efficiency, and the transfer function, right? And then this is also the integration from the smallest size to the largest size. And then it's the same for the data inversion, that you need to require some inversion matrix, right? And then for this system, after I joined the group, actually I was mainly working on developing this inversion matrix and then comparing these FIMs with the SMPS system. So you can see, basically we use the Toomey-Markowski algorithm, right, to calculate the size distributions, and then to consider these different efficiencies, and then to calculate what's the size distribution. So here is the exciting part. We compare the FIMs against the SMPS measurement. So here we're introducing aerosols with different sizes or different size distributions, and comparing the SMPS result that's collected after 1 minute of scan, and then the FIMS result that's also collected over 1 minute, but now you have 60 or 600 size distributions, okay? So we basically calculate the size distributions and compare that against the SMPS. And you can see there's actually very good agreement between these two instruments. But the difference is that over this 1 minute, the SMPS only have 1 scan. As in, the FIMS has 60 size distributions, because when we operated, we were using 1 Hertz as the, let's say, the measurement frequency. Right? So you can see there's excellent agreement. So then we further deployed our instrument nearby a road in Brookhaven National Lab. That's where the instrument was first invented or assembled. So then we compared basically the size distribution, and as you know, the size distribution, if you integrate it, you get the total concentration, right? So we compared the total concentration that's derived by the FIMS against the CPC. So you can see these two again agree really well. But now the things that basically the more information you get from these measurements is that now you can get the size distribution for each 1 second, right? So here is the measurement over 600 seconds, that's 10 minutes, right? So you can see for each second, you get a size distribution. And on the y-axis here, it's showing the aerosol size. And you can see this concentration dip over around 400 seconds is because of some transport of the Aitken mode aerosols. Maybe there's some dilution or some other mechanisms, right? So because these instruments, this FIMS instrument can do high time resolution measurement, it has been applied in so many aircraft measurement campaigns, because people really need this instrument to do submicron aerosol size distribution measurements. And the SMPS, as we introduced earlier, is not sufficient to do these high time resolution measurement, especially if we want to do it accurately, right? So it has been deployed in the Go Amazon campaign, in the Amazon forest, right, on the aircraft, high scale in central Oklahoma, and the ACNA, that's over the eastern North Atlantic on Azores Islands. And then in 2019, I was in the Philippine campaign that's hosted by NASA. It's called the CAMPEX, okay? And I'm pretty sure that there will be furthermore or even more deployments of the FIMS on these research aircrafts. So similarly, we did the comparison between the CPC and the FIMS, integrated FIMS concentration. And then here you can also see, basically during the aircraft measurements, this is showing you a 15-minute measurement, right? So you can see over some periods, you can see these strong spikes of the CPC concentration. If you look at their time scale, right, this only happened within 1 minute, right? So if you measure with the size distribution, you're just going to get, let's say, some measurements here, some measurements here. The whole sample, you're not going to make too much sense out of the results. But with the FIMS, you can get what is going on in each second, right? To look at what is really happening to the size distributions, right? So you can see this intense peak here is caused by some new particle formation, and then maybe some pollution events, right? This huge peak here is caused by these Aitken mode, which might be some urban transport pollution, right? So that's why the FIMS is very helpful in identifying these episodes of strong, like intense aerosol formation. And during the ACNA campaign, we also used this FIMS instrument to monitor the aerosol size distribution, especially to study the new particle formation mechanisms in the atmosphere. So then we're going to introduce some other forms of the DMA that are targeted for different uses. So as you can see, the SMPS is kind of bulky, right? And the FIMS is even bigger, right? Because you need a long column to classify the aerosols. So there's a trend that if we want to do more, let's say, air quality monitoring with a denser network, then we need to make them smaller. We need to make them cheaper, right? So one exploration is to make these radio DMA. So this was invented by Rick Flagen's group at Caltech. So instead of having these two columns, what they did is that they introduced a clean sheet flow from, let's say, if you imagine there's a disk, right? So this is the axis and this is a disk. So the sheet flow is being introduced from the outer region, outer ring of the disk, right? And there is a classification zone between the top plate and the bottom plate. And then the aerosols are being introduced from these like tangential inlet here, right? And then because of the electrostatic force that's being applied between these two plates, then you can separate particles based on their electrical mobility. And the sheath flow are producing a radial velocity of the aerosols towards the center. And then you could classify them based on their electrostatic or based on their electrical mobility, right? So in this way, you compact the size of the DMA, right? This is called the radial DMA. So there are also other ways to monitor, let's say, the ions or very tiny particles, right? So we mentioned that the SMPS system can't really measure very, very small particles, okay? So because the long column or the nano column, the long column DMA or the nano DMA, they have some this diffusion broadening effect of the transfer function, right? And also it uses the scanning mechanism that you can't really have a high time resolution for the measurements. So there are these instruments called the ion mobility spectrometer, right? So where you introduce the aerosols from this inlet here, and at the same time you introduce a sheath flow, right? That's going across or going against the aerosol flow, okay? So we call this drift flow, okay? Basically this system is also called the drift tube to monitor the aerosol size distribution, especially the ion size distribution. So basically if the particle do not have a high enough electrical mobility, they will just be carried by the drift flow and get exhausted. So there is an electric field that accelerates the aerosols, right? So for each ring here, you use a different electrostatic or they use a different voltage. So you accelerate the aerosols, and then eventually they reach to the outlet, and then they're being detected by the electrometer. So basically, for this drift tube here, you introduce the aerosols as pulses. You introduce a pulse of the aerosol flow that contains larger particles, smaller particles, but then based on the time for the particles that eventually reach to the electrometer, right? That's related to the electrical mobility, right? And further related to the particle size or the ionic size. And then the current that's collected by the electrometer is related to the concentration of these aerosols with different sizes, right? So here are some more detailed schematic diagrams of the drift tube, right? So you can see basically you introduce the aerosols here, and then you have different rings that where you have the voltages being added on them. And then you have an exit here to connect to a detector where you find or detect these aerosols. So basically, this is how the drift tube looks like, and then there are some more studies related to how the flow, the streamline looks like, or the electrostatic or the electric field looks like in the system to achieve a better or more accurate measurement of the ion mobility distribution, right? So I'll just skip these contents here. Feel free to read these manuscripts or articles listed here, right? So here I also want to talk about the high resolution DMA measurements, right? So the eye mobility spectrometers can give you the, let's say the size distribution of ions, but the aerosols has to be introduced in the pulsed mechanism, right? If you don't have them in the pulsed mechanism and the flow is continuous, then you're going to have a mixture of aerosols with different sizes reaching the electrolyte. What if we want to get like a continuous measurement of the aerosols? So we still need to go back to the original DMA design. So we introduced that the long DMA or the nano DMA are struggling for the smaller particles because of the diffusion. But if you look at the dimensionless number that are being involved in this classification, then we'll say it's a Peckley number, right? It's related to the flow speed or the aerosol speed or their velocity multiplied by a dimension factor divided by the diffusion coefficient, right? So in order to suppress the diffusion coefficient, you have to increase the velocity of the particles. So that's where the ideas for these high resolution DMAs come out. So basically for these high resolution DMAs, we use a very strong sheath flow. They can go up to 200 liters per minute, and some of them can even go to, let's say, 1,000 liters per minute, right? So basically they're limited by the critical distance that are, let's say, the gap between these two cylinders, because the velocity is limited by the choked speed, right? The choked flow, where the speed of the flow cannot be higher than the speed of the sound, right? So basically here, we can use a higher sheath flow rate, and then this will reduce time for the particles to diffuse between these two electrodes, and then you can get much higher size resolutions when you're detecting these very small particles. So for example, here we did a comparison between the half mini DMA, which is one type of the high resolution DMAs, and the nano DMA. So you can see when we're detecting these ionic clusters with specific sizes, right? The half mini DMA really has a very high sizing resolution compared to the nano DMA, right? So if you want to know more about the high resolution DMA systems, you can read these papers. So the half mini DMA system was first manufactured by Juan de la Mola at Yale University. So currently in my group, I have Shanakia, Bhagia Ramesh, working on these, let's say, the flame ions or the new particle formation under high temperature environments. And we use these high resolution DMAs to monitor the size distributions of these incipient particles, okay, that are below 3 nanometers. So here there are more information regarding what are the Reynolds number limitation for different types of the DMAs, and then also about their resolutions for monitoring these species or these particles. So finally, I want to introduce the tandem differential mobility analyzers. So the tandem means things are being arranged in series, right? So tandem DMAs just means that you're using 2 DMAs to do some measurements. So people use these tandem DMAs or TDMAs to monitor aerosol hygroscopicity, volatility, or charge distribution. So how do we do that? How do we monitor the hygroscopicity? As you know, the hygroscopicity is basically dependent on how much the particle absorbs water vapor, right? So when you go to humid environments, for a hygroscopic particle, it's going to grow in its size because they are absorbing water vapor, right? They like water vapor. But then for the hydrophilic particles, they don't, or the hydrophobic particles, they don't collect water vapor, so they remain their original size, right? So the hygroscopicity plays an important role when you are talking about the aerosol cloud interactions, because if the particle is more hygroscopic, it can obtain more water vapor. So it's easier for these particles or for these aerosols to form cloud droplets, right? And further influence the Earth's climate or the energy budget, right? So to do this hygroscopicity measurement, we have to let these aerosols interact with water vapor, right? And also a lot of times the hygroscopicity is dependent on the size of the aerosols. For example, if you have a very tiny aerosol, as we said earlier for the CPC, right? The CPC is very difficult to detect them because there's this Kelvin effect that prevent these particles from growing further, right? You're going to require more supersaturation to grow them. So particles of different sizes have different hygroscopicity. So what we can do is that we can use the one DMA to classify aerosols of a specific size, for example, 100 nanometers, and then send these aerosols through a humidifier, right? So to basically let these aerosols interact with water vapor, and further, we can classify their size distribution or to measure their size distribution with a second DMA. So if the aerosols absorbs water vapor and then they're going to grow to larger sizes, then you can see that from the size distribution measurement in the second DMA, right? So it sounds quite straightforward, but there are a lot of factors you need to consider. So first, you have to dry the aerosols, right? You don't want to introduce wet aerosols directly. You want to give all of these aerosols a same starting relative humidity. And also inside the second DMA, you have to condition the relative humidity for the sheath flow as well, because if the sheath flow is dry, right, then you're going to dry these aerosols again. You don't have the grown particle size distribution. So because of that, you need to introduce these water bubblers or water baths that basically you provide high humidity air, and then they're used to humidify the aerosols and also the sheath flow. And these relative humidities for the aerosol flow and the sheath flow have to be the same, right? And then you can do these hygroscopicity measurements. So here I'm just showing you some papers. This one is a very important one, talking about how to use a TDMA to study the particle growth or evaporation. So similarly, the volatility, right? So hygroscopicity is how it takes water vapor. Volatility is how the particles lose components under high temperature. So instead of using a humidifier, you could just use a heater, like a furnace, right, to increase the temperature. And because of that, you also need the DMA to be operated with relatively high temperature, okay? And we could even use that for charge distribution measurement. So I think I showed before that basically for the charge distribution, there's both a field theory where you can calculate the charge distribution, but people also did experiments to monitor or to determine the charge distribution. So to do that, you replace a humidifier with a neutralizer. So if you imagine, if we send in 100 nanometer particles, and inside the neutralizer here, the charge is going to get redistributed, right? You're going to basically have some particles, some 100 nanometer particles with +1 charge, some of them with +2 charge, some of them with -1, some of them with -2. And in the second DMA, you can see how their size distribution look like. So for the doubly charged particles, you're going to detect them under lower voltage because now they have a higher electrical mobility, right? And further, based on the concentration you see from the DMA, then you could know what is the basically what is the charge distribution, or directly calculate what is the charge distribution of the aerosols. Okay, so here I also have another paper talking about the method for measuring the charge distributions. So here I'm just showing you one paper talking about the hygroscopicity measurements using the FIMS that we used earlier, right? So after the FIMS was developed, so there's also efforts to change the working fluid from alcohol to water, right? So one advantage for changing that is there are safety concerns that you don't want to use the alcohols, but after changing the working fluid to water, you can now start to measure the hygroscopicity because it's very easy to control the relative humidity in the sheath flow, right? Since you already have water to grow these aerosols. Okay, so basically here, this is a study showing how the aerosol size distribution change when we change the relative humidity of the sheath flow. So you can see when it's at 75% RH, right? So you still have this size distribution, but when the RH further increases, you start to have these two different peaks. And here we were introducing sodium chloride to the tandem DMA, right? So first classify particles of 100 nanometer and then send it to the FIMS. So by using this information, we could find out, and actually the reason why you see two different peaks is because of the deliquescence of the salt, right? So you can see basically here, this is our results, and then we were comparing that against some theoretical results, right? So the deliquescence is a process where the aerosols suddenly absorb, or salt suddenly absorb enough of water vapor that they grow into tiny droplets, right? They have a huge expansion in their volume, right? So then we could also apply this method for measuring the ambient aerosols. For example, we introduced aerosols with different sizes, and you can see basically they have different size distributions, right? They shift to the larger sizes. So from these size distributions, you can find out that aerosols have different hygroscopicity, right? And also you have different peaks here, which means that there are some mixing effect where different components are existing in particles with different sizes. So based on these grown sizes, you can plug them into this equation to find out what is the hygroscopicity of these aerosols. So here, this is a Kappa-Kohler theory that was discussed in this Patterson-Kreidwitz paper in 2007. So they were trying to find a single parameter to predict the hygroscopicity of the aerosols. And that is related with the dry aerosol size and then the grown aerosol size under certain relative humidity, okay? So based on these parameters, you could calculate what is the hygroscopicity parameter, hygroscopicity value, and then further to predict what is the cloud forming potential of these aerosols, okay? So that's it for this class. So this class, we basically introduced different types of the DMA systems for measurements of different purposes. And so you can see the SMPS system or DMA system is widely used for the aerosol research, right? You can not only measure their size distribution, but also other properties of the aerosols, okay? So that's it for this class. Feel free to let me know if you have any questions. All right, thank you.